Now we see how to find the electric field due to a quadrupole at an axial point, when the point is on the axis. We want to find the electric field due to a quadrupole at a point on the axis of the quadrupole, electric field. We can proceed from the last lecture. We already found electric potential due to a quadrupole at an axial point. Due to a quadrupole at an axial point, we know, we have studied how to find the potential. Now we can use this relation, E is equal to minus dV by dr, to find the electric field from the potential expression. This is a special case when the point P is far off. So simply find minus dV by dr, where V is this. We are taking the point to be far off, a distant point. We assume the point P to be far off. You see here, R by A very much greater than 1. That means R is very much greater than A. R is very much greater than A means point P is far off, and we got this expression after applying the approximation. So what now we have to do to find the electric field? To find the electric field, of course, you can directly find electric field without using this expression. So find the electric field at P due to this dipole. See, we know that a quadrupole is after all what? Two dipoles with same dipole moment but having opposite directions for the dipole moments. This collection, this arrangement of the two dipoles is known as a quadrupole. So what is a quadrupole? Two electric dipoles. We are talking about the electric quadrupole. Two dipoles arranged opposite to each other. Dipole moments opposite to each other. That assembly, that arrangement is called quadrupole. So in this case, this is a quadrupole. So this minus q and plus q here. This is a dipole with a dipole moment this way. So find electric field using electric field due to a dipole at a far off axial point case. Again find the electric field at P due to this dipole, because there is one minus q and one plus q, one dipole. One minus q and plus q, another dipole. There is minus 2q here. You consider minus 2q as minus q and minus q. One minus q consider with this, another minus q you consider with this. So one dipole moment is this way, another dipole moment is this way. The dipole moments are opposite. This arrangement is a quadrupole. So you find the electric field directly at P if you want. That is, find electric field at P due to each of the dipoles and use principle of superposition to combine them. Find the vector sum. Otherwise, now because we already found the electric potential, it won't be much difficult for us to find the electric field at an axial point which is far off from the quadrupole. So what we have to essentially do, find minus dV by dr of this expression. So what we can now do is this. Okay, I just remove this. V for a distant point kq by r cube. Note that this q is not charged, this q is quadrupole moment. Already it is given there, 2a square q is capital Q. This is quadrupole moment, so don't get confused. So now E is minus dV by dr. This of course you can write kq r power minus 3. So this is minus dV by dr, you know, minus of kq r power minus 3, kq constant. You can write like this also, and minus kq outside, r power minus 3, differentiation of r power minus 3, x power n, differentiation n into x power n minus 1 if you differentiate with respect to x, r power minus 3 differentiate with respect to r, x power n, n into x power n minus 1, n into minus 3 into x power r power n minus 1, so minus 4. So minus 3 and minus symbol, so two negatives are there, so that will become plus. So K 3Q by R power 4 is a numerical value of the electric field. So electric field intensity due to quadrupole at an axial point 3kq by r power 4. Q electric quadrupole moment 2a squared into q. A is the distance between the charges in a given dipole, or distance between the charges in a dipole, that is between one positive charge and the negative charge. That distance is A. So final expression for the electric field intensity is this. So minus dV by dr you can use to find the electric field intensity. This is for a distant point. Okay, thank you.